Hello again, everyone, and thank you again for joining. It's a pleasure to see you all here. Um, my name is Rick Frage, Sales Manager at SFTec. This webinar is, as you can see, is design of cantilever retaining walls using FRP, fiber reinforced polymers. Uh, this is, as you know, some of you have been regular attendees to our webinars. This is one of many webinars that we're holding regularly on a monthly basis that talk about different structural elements that can be designed with FRP. This webinar is about 45 to 50 minutes. That leaves us about 10-15 minutes for Q&A towards the end. I recommend that you keep pen and paper ready. This will be a technical webinar. It will have some calculations and formulas that we will be discussing. We will also try to address as many questions as we can towards the end. So please, if you have any questions, send them to us through the Q&A icon at the bottom, and we will try to address it towards the end. At the end also, I'll be sending you a quick survey. It's a very short survey, will take less than a couple of minutes. And we'd like to have your feedback and appreciate it. And also if you'd like to receive a certificate of participation, there's a question there in the survey. You can tick yes, and we will be happy to send you a certificate of participation. So before we start the webinar, I would like to introduce Dr. Ahmed Salama. Dr. Ahmed Salama has been the speaker of these webinars for some time. I believe this is probably the 6th webinar. So anyways, Dr. Ahmed Salama has a bachelor's of engineering and master's degree in structural engineering from the University of Cairo in Egypt. He worked in the Egyptian Ministry of Water and contributed to several projects during his employment there, like the Al Sharika bridges, Ismailia Canal project. So he's the right one to speak to you about the retaining walls for sure. He came to Quebec, Canada, and after being admitted to the Ph.D. program at the University of Sherbrooke, to continue his studies in structural engineering under the supervision of Dr. Brahim Benmokrane. He specialized obviously in concrete structures that are reinforced with fiber reinforced polymers. He joined SFTec in around July 2019. He worked on several projects with SFTec in different industries. He did telecommunication tower bases, water purification stations, different slab projects, ICF walls, tilt-up walls, you name it. I will give him the mic now, and hopefully you would be enjoying the webinar. Thank you very much again, and Ahmed, Dr. Ahmed, the mic is yours.
Okay, thanks a lot, Rick, for this great introduction. I highly appreciate it. So again, welcome to all of you from different parts of the world and different time zones. This gives me pleasure to see a good presence here in our webinar. Please stay with us and we all will learn together. Today, we are going to talk about design of a cantilever retaining walls using fiber reinforced polymer bars. In the next slides, I will go through brief introduction, field application with FRP bars, and finally, design of FRP reinforced concrete retaining walls. In the beginning, I would like to introduce our company, SFTec. Who are we? SFTec is a professional entrepreneurial industry in the business of the composite rebar. What do we do and who do we work with? SFTec is working closely with national and international engineering firms and the government departments in the construction of parking facilities, water treatment plants, and retaining walls, as well as other structural elements. What is our focus? SFTec is focusing on the market of FRP rebar applications in North America and beyond through providing a complete design for new structures reinforced with FRP bars and conducting research and development strategies to ensure continuous improvement of SFTec products. The question now, what is the composition of FRP materials? As per the microscopic analysis here on our right side, FRP materials consists of fiber reinforcement, polymer matrix, and the interface between the fiber reinforcement and the polymer matrix. FRP materials may be bars or sheets. We are using the FRP bars as a creative solution to eliminate steel corrosion problems, while FRP sheets, for strengthening and rehabilitation purposes. In our presentation, we will focus on FRP bars. So, what are the types of FRP bars? In the market, we have four main types of FRP bars: carbon, armed, glass, and basalt. However, GFRP bars have recently gained a wide acceptance as a practical construction material for new constructions due to their cost effectiveness than other types of FRP bars. As we see here in this slide, the typical stress-strain curve for steel and FRP bars. There is only difference between steel and FRP bars is that FRP bars are linear up to failure and exhibit no ductility or yielding. SFTec products. In our company, we are mainly focusing on the production of GFRP materials as straight bars, bent bars, closed loops, spirals, and GFRP shear connectors for sandwich panels. Why you should use SFT bar instead of steel bars? In the last 10 years, the FRP rebars have been used successfully in hundreds of bridges, parking lots, tanks, and marine structures across Canada and US. FRP materials offer many advantages over the conventional steel bars, as longer service life, improved durability in harsh marine environments, the advantage of corrosion resistance, high tensile strength compared to the yield stress of steel, lighter than steel, no corrosion even in harsh chemical environments. Finally, neutrality to electrical and magnetic disturbances. Now I will talk about retaining walls. What is a retaining wall? Retaining wall is a structure to retain soil, rock, or other material in a vertical condition. So it provides a lateral support to a vertical slopes of soil that would otherwise collapse into a more natural shape. What are the types of retaining walls? Number one, cantilever retaining wall. It consists of vertical wall called stem, heel slab, and toe slab. All elements of the cantilever retaining wall behave like a cantilever beam of a slab. It is suitable up to 6 meters. It may be T-shaped or L-shaped. Number two, counterfort retaining wall. In this type of retaining wall, the stem and the heel base are tied together by a counterfort at a suitable intervals. It is suitable and economical for a height more than 6 to 8 meters. Number three, bridge abutments. This kind of walls is similar to cantilever one, but the top stem is braced by the deck slab of bridge. Number four, box culvert. This one acts as a closed rigid frame consisting of a single or multiple cells. It resists lateral pressure of earth and vehicle loads. Now I would like to shed the light on our field application. The first field application we have here is the first worldwide waffle slabs reinforced with GFRP straight and bent bars in Araya project. Another example, as we see here on our right side, for casting slab on grade in Nova Scotia, Canada. Another application for using GFRP shear connectors in precast sandwich panels at one of IBM buildings. Another example here on our right side for GFRP reinforced concrete retaining walls supporting GFRP reinforced concrete ground slab for the city of Montreal. Finally, we have another great field application with our GFRP bars in reconstructing the reinforced concrete wave wall. For your information, the wall length is 55 meters, while the wall height is 3.1 meters. Today, we are going to deal with the design of this wall in detail in the upcoming slides. Now I will shift to the design of FRP reinforced concrete retaining wall. It is worth mentioning that several codes and guidelines are available around the world for design of structural elements reinforced with FRP bars. In this slide, and as I said earlier, we will go in detail for the design of this retaining wall. So here it is required to redesign this damaged reinforced concrete wave retaining wall using SFT GFRP bar. The consultant suggests the dimensions and soil properties as shown below. From the geotechnical report, the density and the internal angle of the backfill soil are 20 kilonewton per meter cube and 28 degrees respectively, while the allowable soil pressure is 240 kilonewton per meter square. The concrete compressive strength equals 32 MPa. The live load surcharge on the backfill, as we see here, equals 40 kilonewton per meter square. A reinforced concrete slope protection is shown in the front of the wall, as surrounded by this dashed line. It is therefore required to design this wall for flexure and shear to retain the backfill here. As per the design codes CSA A23.3 to the year 2014 and CSA S806 to the year 2012 were applicable. The first step here is to calculate some properties related to soil and concrete. As given, the concrete compressive strength equals 32 MPa, so the elastic modulus is simply 4,500 by the square root of the concrete compressive stress. The stress block parameters alpha 1 and beta 1 can be calculated using these two equations. So alpha 1 equals 0.8 and alpha 2 equals 0.89. As given, the internal friction angle of the backfill soil equals 28 degrees. So the coefficient of active earth pressure can be calculated according to Rankine theory using this equation, while the coefficient of sliding friction between concrete and the backfill soil can be calculated using this equation. Step number 2 is to determine the loads acting on the retaining wall. Let us start with the lateral loads. The lateral loads B active 1 due to the surcharge is QK active by the height of the soil. The lateral load B active 2 due to soil pressure equals the area of soil triangle by the coefficient of active earth pressure. The lateral passive earth pressure due to water in front of the wall equals the water triangle area. Now we are going to calculate the acting vertical loads. The vertical loads V1 due to the weight of the wall equals gamma concrete by the wall area, which equals 98.64 kilonewton per meter. The vertical wall V2 due to the weight of the backfill, the dotted area here in the back of the stem. So V2 equals gamma soil by the area. The vertical load V3 due to the weight of the reinforced concrete slab protection is gamma concrete by the area of the slab, which equals 70.08 kilonewton per meter. The vertical load V4 due to the acting live load surcharge equals 40 kilonewton per meter square. Note the vertical load V4 due to live load surcharge and the lateral load due to the passive earth pressure BB here from water will be ignored for stability calculation. So why? In order to achieve the highest overturning moment and the sliding force. After calculating the loads acting on the retaining wall, we have to check the wall stability. The first check we have here is a check for overturning moment. As we see here at the back of the wall, the lateral loads B active 1 and B active 2 tends to overturn the wall, while the vertical loads V1 and V2 due to the weight of the wall and soil tends to stabilize this wall by taking the moment For the lateral loads BA1 and BA2 around the point O here at the end of the toe, we will get the overturning moment value. And also by taking the moment at point O for loads V1 and V2, we will get the stabilizing moment value. The factor of safety for overturning equals the resisting moment value over the overturning moment value, which is greater than 1.5. So the wall is safe against overturning. The second check we have here is a check for sliding. The lateral loads B active 1 and B active 2 tends to slide this wall, while the vertical loads V1, V2, and V3 of the slope protection tends to resist the wall sliding. The factor of safety for sliding equals the resisting force over the sliding force, which is greater than 1.5. So the wall is safe against sliding. Let us go with the third check. The third check we have here is a check for soil stresses under the wall base. Here we will consider two cases. The first case, live load surcharge is not included. The location of the resultant of all acting loads on the retaining wall with respect to point O can be calculated as follows. That the eccentricity with respect to point O equals 0.53. By using the normal stresses equation, the maximum and the minimum stresses at the base ends can be calculated. So Q maximum equals 80.84 kilonewton per meter square per meter, which is less than the allowable bearing capacity of the soil. And Q minimum equals 3.87 kilonewton per meter square, which is greater than 0. So here we don't have any tension stresses on the soil. The bearing pressure without surcharge is shown here on our right side under the base of the wall. Let us go with case number 2. Case number 2 here, live load surcharge is included. The location of the resultant of all acting loads on the retaining wall and the eccentricity with respect to point O can be calculated as follows. What I did here, I included the moments due to the surcharge and I included the weight of the surcharge in order to include the live load in my calculation. The maximum and the minimum stresses can be calculated using the normal stresses equation as before. So Q maximum equals 76.83 and the Q minimum equals 30.73 kilonewton per meter square. On our right side, we can see the bearing pressure with including the surcharge. We will use these stresses in the flexural design of the wall. In this step, number 4, we are going to analyze all wall sections in order to estimate the maximum bending moment and maximum shear force. Let us start with the heel slab. The heel slab acts as a cantilever projecting from the back face of the stem. As we see here on our right side, the heel slab has two different depths. Depths at section 1.1 and the depth at section 2.2. So we will analyze these two sections. For here, section number 1, the acting loads are the surcharge, the backfill soil, and the own weight of the heel slab at section 1.1. The weight of the heel slab at section 1.1 equals 6 kilonewton per meter. The weight of the soil acting on the heel slab at section 1.1 equals gamma soil by area soil, this area, this triangle. The weight due surcharge equals the surcharge value by the effective surcharge length. The effective surcharge length here equals 0.5 meter or 500 millimeter. The maximum shear force at the face of the heel slab equals the summation of V, of the vertical loads, due to surcharge, due to soil, due to heel weight, while the maximum moment due to these loads equals 12 kilonewton meter per meter. A factor of safety 1.6 is taken for calculating the maximum shear force for heel section 1-1 here. Also, the same factor of safety is taken for calculating the maximum bending moment. And as we see here, this is the final shape of the maximum factored bending moment. Now we are going to deal with heel section 2-2. For heel section 2-2, the same procedure was followed to calculate the acting loads, service shear loads, and moments. Finally, the ultimate shear force equals 167.36 kilonewton per meter, while the ultimate moment equals 83.82 kilonewton meter per meter. And as we see here, this is the shape of the bending moment diagram at section 2-2. Now we are going to analyze the toe slab. The toe slab also acts as a cantilever projecting from the front face of the stem. For toe slab, the acting loads are the own weight of the toe slab and the upward reaction of the soil. The weight of the toe slab can be calculated by multiplying the area of the concrete density by the area of the toe, area of this part. At the face of the toe section, the bearing pressure Q1 can be calculated from similarity. The soil pressure here under the toe section will be divided into two shapes. The first one is a triangle and the second one is a rectangle. So we have two forces here, one for the rectangle and one for the triangle. The maximum shear force at the face of the toe slab section equals the summation of V1 plus V2 minus the weight, the downward weight coming from the weight of the toe, while the maximum moment at the face of the heel slab equals 42.94. As we did before, a factor of safety 1.6 is taken for calculating the maximum shear force, and also the same factor of safety is taken for calculating the bending moment. So here we have the final bending moment shape for the toe slab. Now we are going to analyze the stem section. The stem also acts as a cantilever from the base of the wall. As we see here on our right side, the stem has two different depths, at section 1-1 and at section 2-2. So we are going to analyze these two sections. For section 1-1, the active earth pressure B1 and B2 due to surcharge and soil will be calculated at the selected depth. So we will stop here at section 1-1 and calculate B active 1 and B active 2. So B active 1 equals 24.48 and B active 2 equals 10.4. The maximum shear force at the base of section 1-1 equals the summation of B1 and B2. And the maximum moment at the face of the stem of section 1-1 equals 26.70 kilonewton meter. A factor of safety 1.6 for the shear force and for the bending moment is taken into consideration. And here, this is the final shape of the bending moment diagram. For stem section 2-2 at the base, the same procedure was followed to calculate the acting loads at this height of section 2-2, and the maximum shear and maximum moment were calculated, and finally the ultimate shear force equals 78.85 kilonewton per meter, and here is the final bending moment diagram for the factored moment. In step number 5, we will calculate the transverse flexural reinforcement for the analyzed section. For the maximum positive bending moment of section 1-1 of stem, assume using 7 bars number 7 per meter run. For the maximum positive bending moment of stem section 2-2 and the heel section 2-2, assume using 7 bars number 8 per meter run. For the maximum negative moment of heel section 1-1, assume using 7 bars number 5. For the maximum positive bending moment of the toe section, assume using 7 bars number 5. In the table here, we have the wall section and the thicknesses, and corresponding to each section, we have the assumed transverse flexural reinforcement. Now we are going to calculate the flexural depths. So the flexural depths can be calculated by subtracting the clear concrete cover and half the bar diameter from the total thickness of the section. So the flexural depths of all sections are presented here in the third column of this table. Now, the flexural reinforcement ratio can be calculated using this equation, where B equals 1 meter. The flexural reinforcement ratio for all sections are presented here in the fifth column in the table. The balanced flexural reinforcement ratio for all sections equals 0.26, and this calculated according to the Canadian standard CSA S806 to the year 2012. By comparing the flexural reinforcement for every section with the balanced flexural reinforcement, all sections are compression controlled sections, and this is the required mode of failure according to the Canadian standard. In step number 6, we will check the flexural moment capacity versus the factored moment capacity for all analyzed sections. Let us start with the stem section number 2. The maximum positive moment at the face of the stem section equals 76.51 kN. The flexural moment capacity can be calculated using this equation according to the Canadian standard S806 to the year 2012. All variables here in these equations are known or calculated before, except the neutral axis depth C. So from equilibrium, we can get C. Therefore, C equals 212.69 millimeters. Before calculating the flexural moment capacity, we need to check the ratio between the neutral axis depth and the effective flexural depth, and this ratio should be greater than this value. This value equals 0.159. The flexural moment capacity by substituting with all variables in this equation is 3,836 kN. By comparing the flexural moment capacity and the maximum factored moment, the flexural moment capacity is greater than the maximum factored moment. The cracking moment can be calculated using this equation for stem section number 2. So M crack equals 1069.50 kilonewton meter per meter round. By comparing the flexural moment capacity and 1.5 M crack, the flexural moment capacity here exceeds 1.5 the cracking moment capacity and satisfies the minimum reinforcement condition for the Canadian standard S806 to the year 2012. Here in this table, we are going to check the flexural moment capacity for all considered sections. First, the neutral axis depth is calculated for each section from equilibrium. Then C over D value is checked with this value as we calculated it before. After that, the flexural moment capacity is calculated according to the Canadian standard S806 to the year 2012 using this equation. And the flexural moment capacity is checked for every section with the factored moment capacity. And as we see here in this column of the table, all the factored moment capacities, all the flexural moment capacities are greater than the factored moment capacity. And finally, the M crack is calculated for every section. We have already analyzed it. And the flexural moment capacity is checked with 1.5 from the cracking moment capacity. And as we see here in all sections, the moment resistance, the M resistance or the flexural moment capacity exceeds 1.5 M crack. As I mentioned in the previous webinars, in order to have a successful design for any structural element with FRP bars, you should check the serviceability limit state. In order to do that, we have to check. So we will apply these checks on our retaining wall. So the first one is to check the maximum stress and strain in the FRP bar under full service load. The maximum stress of the FRP bar under full service loads can be calculated using this equation. And the value from this equation should be less than or equal to 25% of the FRP bar ultimate strength. The maximum service moment value is 47.82 kilonewton meter per meter run, and this comes from analysis. All factors in these equations are known or calculated before, except the factor K. The factor K is simply calculated from this equation, which depends on modular shear ratio and the flexural reinforcement ratio. The modular ratio is simply the ratio between the elastic modulus of the reinforcing bar to the elastic modulus of concrete. The flexural reinforcement ratio is 0.272%. So rho F by NF equals 0.00694. And finally, the K value equals 0.111. The maximum stress in the used bar under full service loads equals 10.59 MPa, which is less than the 25% of the FRP bar ultimate strength. We checked the stress in the used bar, and the elastic modulus is known for us. So we can estimate the maximum strain under full service load. And the maximum strain under full service load here is less than 0.0015. So no need to check the crack width parameter. Actually, I'm sorry for the title. There is a problem here. It should be design of FRP-RC retaining walls, not combined footing. I'm sorry for this one. In this table, we will repeat all previous steps for all sections to check the stress and the strain limitation for the used bar in all design sections. First, the K factor is calculated for every section using the flexural reinforcement area, the K factor, the flexural depth, and the service moment for every section. The maximum stress for every section can be calculated using the Canadian Standard equation. The maximum stress for every section is checked for the 25% of the ultimate strength of the used bar. And as we see here, the maximum stress is less than the 25% of the FRP bar ultimate strength. The maximum strain in the used FRP bar can be calculated by dividing the maximum strength of the used FRP bar under full service load by the elastic modulus of the used FRP bar. And as we see here, all these values are less than 0.0015. So no need to check the crack width parameter. In step number 8, we are going to check the one-way shear for all design sections. Let us start with the stem section number 2. Here, the effective shear depth equal the maximum of 0.9 from the flexural depth or 0.72 from the thickness of the section. So dV equals 1181.25 millimeters. The maximum shear force and bending moment at the stem face at section 2.2 equals 78.85 kilonewton for the shear and 76.51 for the moment. The allowable one-way shear strength for the concrete according to the Canadian Standard S806 to the year 2012 can be calculated using this equation. We have some important factors here affecting the one-way shear strength. Number 1, the factor Km. Factor Km is a coefficient taking into account the effect of moment at critical shear section. The factor Kr is a coefficient taking into account the effect of reinforcement rigidity. The factor Ks is a coefficient taking into account the effect of member size, while factor Ka is a coefficient considering the effect of arch action. Finally, the one-way shear strength equals 866 kilonewton per meter for stem section number 2. By comparing both values, the allowable and the ultimate for the one-way shear, the stem section is safe against one-way shear. In this slide, we will repeat the previous steps for all sections to check the one-way shear for every design section. First, the effective shear depth is calculated according to the Canadian standard S806 to the year 2012. Then, the one-way shear coefficients are calculated starting from Km and ending at Ka. Finally, the one-way shear can be calculated by comparing both allowable and ultimate values of one-way shear for every design section. All sections are safe against one-way shear. In step number 9, we are going to estimate the shrinkage reinforcement in the longitudinal direction and the compression reinforcement in the wall. In addition to the provided main reinforcement with FRP bars, another kind of reinforcement must be provided in the longitudinal direction to control shrinkage and temperature cracking. In accordance with the American standard ACI440.1R for the year 2015, the shrinkage reinforcement can be calculated using this equation. However, this amount is checked with the minimum reinforcement ratio according to the Canadian standard SA806. So, the shrinkage reinforcement from ACI equals 0.191% and from the Canadian standard S806 equals 0.25%. So the shrinkage reinforcement ratio will be taken 0.25% for all sections. Based on the average thicknesses for the stem and heel slab, 7 bars number 7 per meter and 7 bars number 5 per meter are assumed as shrinkage flexural reinforcement for these two sections. As we see here, 7 number 7 for the stem and for heel 7 number 5. While the amount of shrinkage reinforcement based on the constant toe section is 7 bars number 5 per meter run. For the compression steel in the transverse and longitudinal direction at the top of the toe section, 7 bars number 5 are selected in both directions. The selected bars in the transverse direction from the top and bottom will be connected as one piece. So the compression steel here will be compression FRP bars will be connected with the shear key reinforcement to act as one piece. For the compression reinforcement in the transverse and the longitudinal direction at the bottom of the heel section, 7 bars number 5 per meter run are selected in both directions. The selected bars at the top and the bottom will be connected to act as one piece. And here for the top part of the stem, 7 bars number 5 were selected as a compression steel on the other face of the stem. While for the inclined part here of the stem, a straight FRP bar will be placed every 143 mm in both directions. This bar with an adequate development length will connect the FRP reinforcement of the toe section and the reinforcement in the top part of the stem section. Finally, this sketch represents the final details of the design wall using FRP bars. Thank you so much for continuing with us till the end of this presentation.